Hi, this is Robert, and today we're going to go over a system of differential equations and determine how to find the solution to this system. Okay, we need an x equation, x in terms of t and a y in terms of t, that will satisfy this system of equations, meaning when we take the first derivative of the x equation and we set it equal to 10 times the 0th derivative of the x minus 5 times the 0th derivative of the y, we get them equal to each other. And this other equation has to be true. So how can, if we think about possible trial solutions of x of t and y of t being polynomials, for instance, let's just try like second order and first order. We can notice pretty quickly that if you don't have much experience with differential equations, this isn't going to work, right? If we take the first derivative of the second order differential equation, we get a first order. But then when we add the 0th derivative, we get second order minus first order. We're going to get some stuff with second order terms, first order terms, but the left-hand side doesn't have any second order terms. So that's why this fails. If we mess around with different polynomials, we're not going to get a solution here. So what we'd like to see is some stuff in terms of t, maybe, or exponential, some stuff times some constants times e to the at, or in y, maybe some constants times e to the beta t. Exponentials will work quite well, right? When we take this will have a couple of terms, maybe plus beta t, some terms. This might have and this will have an alpha t. If you think about it, right? If you take the derivative of exponential terms, they stay very similar. They just the constants out front change. That's about it, right? We're not adjusting the orders like we would on a polynomial, and so they can add and subtract. The first derivative of this could very well equal various combinations of the 0th derivative of the x plus or minus various combinations of the y, right? Because these will add and subtract, right? The like terms will add and subtract, and it'll work out nicely. So that's basically what you're doing, is starting with the general solution for a differential equation like this, and I'm going to start off with the general form, which we're going to call these eigenvalues. We're going to use the eigenvalue method. Various methods of solving the system, but the general solution we want to use will be this. We're going to determine characteristic equation, and the roots of the characteristic equation will give us our eigenvalues. And each eigenvalue will have an eigenvector associated with it. We can call that eigenvector 1, which has components 1 and 2. And we'll have a second eigenvalue of our characteristic equation. Okay, this is if our characteristic equation has distinct real roots, then we'll have two distinct real eigenvalues. And so this will be the general solution for that, which each eigenvalue has its own eigenvector, which has its own components, x and y components associated with it. So this is going to work for distinct real roots. The general solution for repeated real roots will look a little different, and I'll go over that in another video. And the general solution for complex roots will have exponential factors, but also sines and cosines, as we've been used to seeing it with other methods. So for this video, I'm just going to keep it short. I'm going to show you how quick and easy this method can be, and we have our solution. And if it doesn't take too long, I'd like to prove that that solution works. So by plugging them back in, taking the first derivative of each and showing that these work. So let's just come up with the solution first of all. So first we need to come up with our roots. And the roots come from the roots of the characteristic equation, which come from the determinant of our A coefficient matrix minus lambda I. Set it equal to 0 and solve. This will give us a second order differential equation, or quadratic equation for this. How does that look? Well, let's look at the characteristic. Let's look at the coefficient matrix here. 10, negative 5, 8, negative 12. If these equations are stacked, then we can just write down the coefficients as we see them, with the first column being our x column and second being our y column. That's our A matrix coefficient. So A minus lambda I. Let's do that. Remember, I is the matrix, the identity matrix, 1, 0, 0, 1. So when we multiply lambda times I, we'll get lambda 0, 0, lambda. A minus lambda, or 10 minus lambda, negative 5 minus 0, 8 minus 0, negative 12 minus lambda. Find the determinant of this. That's 10 minus lambda times this. I'm actually going to make that 12 plus lambda with a negative in front, factoring out the negative sign, minus this diagonal, minus a negative 5 times 8, set it equal to 0. Let's solve this equation. We get 120 with a negative in front, 120 minus, or plus 10 minus 12. It's minus 2 lambda, minus lambda squared. Negative times negative is positive 40. Distribute the negative, we get lambda squared minus plus 2 lambda, minus 120 plus 40 is minus 80. Factor this. We have an 8 and a 10, that gives us 2, plus 10, minus 8. And so we have lambda, let's call lambda 1 8 when we set this equal to 0 using the zero factor property. Lambda 1 will be 8, lambda 2 will be negative 10. Here's our lambdas, our eigenvalues. So we have pieces to plug in here for our general solution. Now we just need to come up with these associated vectors, and we're done. Okay, so grab another piece of paper. Let's do that. For lambda 1, we called that, I believe, 8. Yeah. For lambda 1, we have 8. So we jump back to our matrix with the eigenvalues, the general eigenvalues plugged in. We'll plug in 8. We get 10 minus 8, and negative 12 minus 8 is negative 20. This should always happen. Notice this is a scalar multiple. 2 times 2.5 gives us 8, so negative 5 times 2.5 should also give us this negative 20. These are scalar multiples of one another, so we just choose either row to figure out the associated eigenvector, which has components k1 and k2. k1 the x component, k2 the y component. And so now with any vector, the general solution will work if we have any scalar multiple of that vector. So if our vector is 1, 2 components, x and y components 1, 2, then 2, 4, 3, 6, anything will work as long as it's a scalar multiple. So that's why we can set this, one of these components equal to whatever we want, to find what the other component is related to that. So 1 is a nice choice, 2, k1 minus 5, so we get 5 halves, right? So let's keep in mind that this is going to be our capital K1 vector, which has components. The x component, 5 halves. The y component, so let's put this in the proper order. Remember, K1 is the x component. Okay, well, like I said, we can scale this up to or down. So if I don't like fractions, I can multiply by, let's multiply by 2. 5, 2. That works. Either of those work, or any scalar multiple, negative 5, negative 2, whatever you want. All right, so we're almost done. Lambda 2 is negative 10. So if we plug in negative 10 into our eigenvalues here in the A minus lambda I matrix, and then find, okay, solve that. So it's negative 10. 10 minus negative 10 is 10 plus 10 is 20. This is 8, negative 5. And then we have negative 12 minus a negative 10. Negative 12 plus 10 is negative 2. Negative 2. Again, scalar multiple. They almost look the same, but not quite. Oh, I'm sorry, I said that wrong. This is times 4 times 4. This is times 2.5 times 2.5. Okay. So, anyways, they're scalar multiples of one another, right? So this is going to, let's pick the bottom row. 8k1 minus 2k2 equals 0. Let's choose, we're just arbitrarily choosing 1. It's a pretty standard choice. So minus 2 equals 0, so we get 2 over 8, 1 over 4 for k1. So our k vector, k2 vector, is 1/4, 1. Or scale that up, multiply by 4, and that works too. So our general solution, our final answer, is up to a constant k1, 5, 2, e to the 8t, whereas, and it doesn't matter if you switch the orders, calling lambda 1, lambda 2 instead, but as long as you keep the associated vector with it matched up, that vector goes with that value, and negative 10 goes with this other vector, negative 10t. So there's our general solution here. Now that should be guaranteed to work if I test that. Remember our original equation that we have. Let's just test one of these here. dx dt equals 10x minus 5y. Let's test that, make sure that works, and you can go ahead and test the other one. So x of t, y of t. These are two vectors here, our two equations. So x of t is the top parts here, the x components. So x of t equals 5c1e to the 8t plus c2 times 1 e to the negative 10t, and y sub t, according to our general solution, is 2c1 e to the 8t plus 4c2 e to the negative 10t. So this should work. These solutions should work. Let's try. Let's look. Derivative of x, we get, derivative of this is 40 c1 e to the 8t minus 10 c2 e to the negative 10t. That should equal, does that equal? Okay, I should have given myself more room here, but that's okay. We'll do that down here. Let's see whether this equals 10 times the non-derivative minus 5 times the non-derivative y. So 10 times this gives us 50 c1 e to the 8t, 10 times this, plus 10 c2 e to the negative 10t, minus 5, so minus 5 times this y. So minus 10 c1 e to the 8t, minus 5, minus 5y, minus, that's what I'm doing, minus 5 that, minus 5 that, minus 20 c2 e to the negative 10t. This is testing our solution. Does this equal this? Well, let's add these up. 50 minus 10 is 40, c1 e to the 8t, check. 10 minus 20 is negative 10 c2 e to the negative 10t. Negative 10 c2 e to the negative t, check. So I'll let you test the other solution, or the other original equation, that the y derivative is equal to the 8 times the non-x derivative minus 12 times the non-y derivative of our general solution. this being our general solution. Or in this form if you like. But that's it. Thank you very much. In the next videos I'll do repeated roots and complex roots. Thank you.